Good afternoon. My name is Randy Rossi. Probably like many people here, I had a Commodore computer as my first computer as a child. So they're special to me. I grew up with them. My parents bought me a VIC-20 to begin with. I eventually moved on to a Commodore 128 and then later the Amigas. Something about these machines inspired me to pursue computer science, so I've been a software developer for over 22 years now. Worked in Silicon Valley and the Greater Toronto area. So this is a story about how my bread bin got its soul back. So in late 2018, a friend gave me this Commodore 64. It was in bad shape. It was damaged in a basement flood. And the risers inside were broken. It was missing a side plate. The motherboard was dead. I ended up fixing the motherboard. I replaced like almost all the RAM chips and a bunch of other ICs. Bought a new case from Individual Computers, transplanted it in there, and saved it. Got a new keyboard as well. So I was left with this shell, and this is the same shell you see outside on the demo floor. I decided to make a replica out of this, and you'll see a lot of people do this on YouTube. You see lots of videos. You got non-destructive mounting kits you can 3D print or buy. Why use a Pi? They're cheap. They're quite capable devices. You can get one for $35. You may have one sitting in your drawer that you just kind of threw in there and never really used or never found a purpose for. There are FPGA solutions if you want to get a replica, but those can get quite pricey. I have a Commodore, or sorry, an Ultimate 64 myself, which is great. You can't really beat hardware, but if you're kind of trying to do it on the cheap, then a Raspberry Pi is kind of the way to go. But emulators kind of get a bad rap, and why is that? So let's take a look at what happens inside an emulator rather than the real thing. What's happening is the host computer is emulating all the CPU, audio, graphics as fast as it can for the next 20 milliseconds worth of audio and video. It prepares a frame, and it waits. And so if you can imagine on a really fast computer, this work can get quite tiny. It might happen in 5 milliseconds. And the rest of that time is just waiting to present that frame to the user. So it's more like you're watching a movie where the frame was generated in the recent past. And emulation has its limitations, and this will come in handy later when we talk about those limitations. So I looked for Raspberry Pi emulators, and I came across this list: Combian, PyLizard, RetroPie, Chameleon Pi, and then these other ones that are also based on the same Linux distributions. So these are all Linux distributions, and they're all running Vice, the versatile Commodore emulator, which is a great emulator. A lot of work went into making the 64 emulator accurate. And some of these emulators are written so that they're dedicated to be a Commodore 64. That's the only thing that they do, like Combian and PyLizard. The other ones are they have more emulator options available. You have Nintendo and Amiga, and they have this fancy carousel interface. I was interested in making a replica for my shell to just dedicate that Raspberry Pi to being just a Commodore 64. So I tried these. I tried most of these, and I wasn't getting the experience that I wanted out of my replica. It really fell short of the real thing once you've used the real thing. I don't know if you've ever used Vice on your desktop. It just doesn't feel the same. So what I'm going to do is talk about the things that annoyed me about my replica after I had put it together with these distributions. So the first thing was boot time. When you turn on your Commodore 64, it's just instant, right? Combian boots directly into the 64 emulator in about 12 seconds on a Raspberry Pi 3, which is not bad, but it's still booting Linux. And it's just a bunch of services and unnecessary startup scripts are kind of stripped away. There's no splash screen, no console at boot time, so you just get a black screen for 12 seconds, and then you get the blue screen. Other distributions like PyLizard, RetroPie, Chameleon Pi, they take much longer. They can take up to 30 seconds, a minute. It's kind of an annoying thing, and that can take away from that instant on experience. So the second thing that you'll notice when you run Vice emulator on your desktop or even on a Raspberry Pi under Linux is, people say that something doesn't feel right, and what they're referring to is the video quality isn't what you're getting on a real Commodore machine. So one of my test cases here for my project was Commodore 100% demo, and the introduction has a bunch of vertical bars that scroll across the screen. So I'm just going to play, this is a slow motion capture of what I took off. The quality is awful, but what you're going to see here is this is running on Combian, and you'll see there's broken bars that appear, and what that is horizontal tearing. And there's really no excuse for that today. The other distributions didn't show horizontal tearing this bad. They didn't show horizontal tearing, but they did show what I call jitters. And what happens, why does tearing happen? It's because you are changing the region in memory that represents that frame partway through the video display's refresh of the display. Or you're telling it to look elsewhere if you're using a double buffer. On Linux, the modern solution to that is use a Wayland server, and then your application will wait for the vertical blanking interval of the display. That's the period after it's scanned the last line before it changes that memory so that you get a full frame with every refresh. But even with that, on the Raspberry Pi on the other versions like Chameleon Pi or RetroPie, I was still seeing what I call jitters. And that comes from a mismatch between the timing that the emulated machine wants to be and your video display's timing. So your video display is usually either 50 or 60 hertz. If you don't change, say, RetroPie's video mode, the default is 60 hertz. So you're trying to watch a machine that's trying to be 50.125 hertz on a 60 hertz display, and it just doesn't look right. So if you run like the Ghostbusters game, that scroll at the bottom, on a real 64, your eyes will just drift across effortlessly. On Linux, on my desktop emulation, it just doesn't look right. So I wrote this smooth scrolling demo. I was hoping to show it here on RetroPie, but the HDMI switch doesn't work, so I'm just going to stick with the MC64 a little later. I wrote this scrolling demo, and you can see that when you run it on RetroPie, it kind of looks jittery. Even if you change your video mode to 50 hertz, you'll get a period of maybe 2 or 3 seconds where it's nice and smooth, and then it looks like it's dropping a frame, and you get jitter, 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 and then you have another period where it's smooth, and that kind of takes away, again, from the experience. It reminds you that you're not using the real thing. Another thing that annoyed me was audio latency. So the 8-bit guy, when he did his review of the 64 Mini, he wrote a small program that did nothing but hold the keyboard, and when you press a key, changes the background color and plays a tone. And he measured the 64 Mini's audio latency to be a whopping 360 milliseconds. Now, I don't know if they've improved that recently. I hear and I look for evidence. I couldn't find that they improved that. I did the same thing measuring Combian on the Raspberry Pi, except I hooked up my oscilloscope and measured from the time that the USB signal goes low, or the line goes, the circuit's closed, how long does it take for the Pi to emit the tone? And it measured by default with no changes being made to the system, or no optimizations, setting changes. You get 250 millisecond delay. Now I was able to drive that down to about 135 by fiddling with some of the settings, because you can change the audio buffer size in Vice. But I started to get these machine too slow warnings, especially on a Raspberry Pi 2. So audio latency is kind of important, because when your character jumps, you want to hear him jump when he actually jumps, not a third of a second later. Similar to audio latency, you have video latency. Now I did the same thing, hooked up the oscilloscope to the composite out of the Pi, and what you're seeing here is these are the frames, composite frames, and did the same thing, measured from the time in this case it's a joystick press on a USB controller. How long does it take for the emulated machine to see that latch, or that virtual latch, has been pressed? And I found that the worst case was 3 frames for USB. The key raw ends up pushing that out, can push that out by 1 more frame, and I have an explanation for that. That's not too bad for a software emulator. The minimum you're going to do is 1 frame. again, the 8-bit guy did his 64 Mini review and found that he had the 67 frames, or found that the 64 Mini was 67 frames of latency, which is quite high. So the Pi doesn't actually do too bad in that respect. The next thing that annoyed me was, well, you're running Linux, right? And you're not just supposed to kill the power when you're running Linux. If you do that, you run the risk of SD card corruption. Because files may be open, the thing might be writing to files. You don't know what it's doing because there's so many services that could be running. There could be a logging service running. On a real 64, there's no exit. You just kill the power. And I think most people just yank the power, even if they're running a Raspberry Pi with Linux, and they just kind of deal with it, and they probably get away with it. That's why people recommend these power block devices. What these things do is they send a signal to your Raspberry Pi to tell it to shut down. And then once it's shut down, you can kill the power safely. The next thing was the Kira. So this is a Kira. It's a great product. What it does is it turns a real 64 keyboard and real joysticks into a USB device for the Pi. So these end up looking like USB keystrokes to the system. I was disappointed though in finding out that this switch actually isn't a power switch. It goes in the slot where in your shell or in your case where the power switch goes, but you switch. It's actually a mode switch. It changes the mapping of the keyboard, and this USB connector isn't for power. It's the connection that you make to the computer that you want to control with your keyboard. So that kind of disappointed me too. So just to recap, these are the things that I was disappointed with, and I wanted a better replica. So I started my project, but before I get to that, the common thread here is you have Linux, right? This is what you're typically getting with Linux distributions. You're getting kernel space, user space. You might get a whole bunch of services running in the background, a bunch of drivers in kernel space, IPC mechanisms, buffer copies, layers and layers of abstraction that can not only increase boot time, but add latency. And this, typically you'll get a gigabyte distribution with something like, a Linux distribution. So it's a lot of bloat. So talked with a friend of mine at work who's also into retro computers, and his advice was, let's just get rid of Linux. That's easier said than done. His advice was to go bare metal. So what does bare metal mean? Well, you write your own kernel, you basically string together all your code that you want to run. The Raspberry Pi bootloader lays that out into memory in location 8000 hex. Sets the program counter there in the ARM core, and you just go. Everything you have to do yourself. Manage memory allocation, talk to hardware, handle IRQs. Now, fortunately, there's a library, an open source library called Circle that he also pointed to me, that my friend pointed me to. And it's an open source bare metal library for the Raspberry Pi that gives you a bunch of routines to do things like talk to the video core. It has a limited USB stack, simple block memory allocator, kind of like the building blocks you would use to do what you wanted to do on the Pi. Without really rising to the level of operating system, there are no processors, there's no IPC, there's a simple cooperative scheduler, but there's no preemptive scheduler. But what happens, you have these dependencies, right? If you try and compile Vice, which has only ever been compiled on some operating system, what happens? Well, if you try to compile Vice with the Raspberry Pi toolchain, your compiler freaks out. It has many missing headers. Vice is relatively dependency free. However, the one thing you can't get away without is standard library. Things like including standard I/O, standard lib, string functions, string conversion functions, memory allocation. Memory allocation would be nice. So it just throws up, and it tries to build an executable. There's no executable format for a kernel. It's just code. So fortunately, another open source library project called Circle Standard Lib takes a fork of newlib, which is replacement standard lib for embedded systems, and glues back into Circle to provide things like file system access and memory allocation. So armed with those two projects, those two open source projects, my plan was to fork Vice, and generally speaking, if you do these 5 things, you too can have your own Commodore 64 emulator. It's really quite, I mean, the architecture of Vice is quite nice. You get a bunch of callbacks. One of the callbacks is, here's a frame, deliver it to your display device, and you just keep repeating that. Audio, same thing, here's an audio frame, shove that into your audio device, however way you do it. So you implement these platform hooks. And so what I set out to do is implement these 5 things. Now UI is actually optional. You don't really need the UI, but you just wouldn't be able to actually type anything on, but you'll at least get that blue screen, and the processor will be running. The 4th item here, where the emulator will ask you to sleep, like that first slide I showed you with how emulators work. It asks your platform or your architecture implementation to sleep for X number of milliseconds. So if you implement those things, you get your Commodore 64 emulator. Many hours later, I'm not going to get into all the little nitty-gritty details about how this all worked out, but I added my own Raspberry Pi architecture device. Wrote my own video driver, and it's not really a driver, it's not really plugging into any sort of framework, it's just my code that talks directly to the video hardware. Same thing for audio. I used Circle's USB stack for input for both gamepads and keystrokes. And for timing, I did something different, which I'll explain a little later. And I did something crazy. I wrote my own menuing system because I didn't really have anything that I could leverage. There's probably something I could have pulled in, but I was getting impatient, and I just wanted something simple to invoke certain actions like load disks, and it eventually evolved into a full-blown menuing system. Okay, so now the fun part, so the results. So this is a video of me turning on my Commodore or my emulator. Let's see if I can see it on here. So this times from the time you hit the power to the time you get the blue screen, and that's 4.1 seconds, which is really nice. I was really happy with that. It contributes to the feeling that you're using the real thing. This is on composite. On HDMI, most HDMI displays take a little bit of extra time to sync to that. They don't even see that the video signal is there, even though it's there. But it is actually booting in 4.1 seconds. So that made me happy. This is what things looked like before any optimization. I ended up mapping out what the boot process looked like. And everything is running on one core here. Circle initializes, then I launch the Vice initialization. I realized that, wait a second, I have 4 cores on the Raspberry Pi. There are 4 ARM cores. So I started to look for opportunities to do things in parallel. And I identified a couple of routines that were taking a long time. And it turns out that it was the resid engines, which is the SID emulation, initializing these huge arrays for the 6581 and 8510 SID chips. And I realized that they could be pulled out because they don't really require anything that's happening here. And I figured out what in Circle's initialization I needed to launch Vice as early as possible. So things went from this to this. So Core 0 starts up Circle. As soon as the SD card reader is ready, I launched Vice, and in parallel, run those initialization routines, and that cut the boot time in half. I also did some tricks in the file system to short circuit some of the things that Vice was trying to figure out about the files that it was loading. For example, it was loading a kernel, and it wanted to know how big the kernel was. Well, the kernel is always 8,192 bytes, so I just kind of short circuit that and cheat the system so it doesn't have to actually talk to the SD card. And that saved a lot of time at boot. So for video, I mentioned I did something different. Instead of listening to what the emulator wanted me to do in terms of sleeping, instead I just wait for the vertical blanking interval of the display and then deliver the frame. Now this is not something new. I'm pretty sure 64 Mini does this. There's another emulator for Windows, another Commodore 64 emulator for Windows called, I'm not sure how to pronounce it, Hawks or Hoax 64. and it has a 50 hertz performance mode, and I'm pretty sure they're doing the same thing, where they wait for the vertical blanking interval of the display before sending the frame. But the consequences of doing that are that your timing of the machine, of the emulated machine, is slightly faster or slower, depending on whether you're NTSC or PAL. And it's as though the CPU cycles are stretched a little bit or squished a little bit. But you get completely smooth video as long as the Pi is able to emulate 20 milliseconds in the case of PAL. If it's able to emulate 20 milliseconds worth of CPU and audio and video in under 20 milliseconds, it's always going to meet that deadline, that real-time deadline. So, so when you run BMC64, it is, in PAL mode, it is running slightly slower. Although I do have a 50.125 hertz non-standard HDMI mode option. So I'm just going to switch over here. Since my HDMI switch isn't working, I'll just switch over to the Pi. Hopefully it will display. Okay, so this is BMC64. Like I said, I wrote my own menu. This is all me. So it tells you what mode you're in, and since the mode or the timing of the machine is tied to the display mode itself, it's important that you match those. You don't want a 60 hertz video display with a PAL machine. You would end up getting a PAL machine that's really fast, and that's not what you want. So part of, let me just take a look here. I'm going to load snapshot. Sorry. Start. Okay, so this is the smooth scrolling demo. I hope it looks good here. Okay, that's what it's supposed to look like. Your eyes just kind of drift across effortlessly. That's what it would look like on a real machine. When I run this on RetroPie or any of like desktop, Linux desktop versions of Vice, it never looks like this. There's always a mismatch. So that's one of the things that I wanted to address is the video quality. The other thing I wanted to make sure that people had the ability to customize the video. So you can squish the display. This is most importantly for composite out. So you can set the aspect ratio and kind of squish things or trim away the border regions so that you can get that box on your CRT in exactly the right spot. So it's more important for CRTs, not so much for HDMI. I think the defaults are fine. You probably want to see the full border anyway. And depending on how much time I have, I might show you some other neat things about the video. So let me switch back to my presentation. Okay, so video quality was pretty good. So being Vice, you also have Commodore 128 emulator, VIC-20 emulator, and +4 emulator, and I will eventually do the Pi, or the PET, I mean. This is an example. This is me playing with layers. The Commodore 128 was an interesting machine. It had 2 displays. So I wanted to make sure people could see both displays at the same time. So you can actually have picture-in-picture modes or side-by-side modes and see both displays at the same time. Okay, next thing was audio latency and synchronization. I made sure that I tried to get the audio buffer as small as possible. I basically shoved that data right into the HDMI stream as quickly as I can through Circle's API, and I was pleased to find out that the audio latency was down under 100 milliseconds, which is I'm happy with. Once you get above 100 milliseconds, it starts to become perceivable, and you can really feel the difference if you run that same program that the 8-bit guy wrote, and you press the key or click the joystick button. You can feel the difference, especially between this and, say, something like the 64 Mini. My test case for this was Ghostbusters. I know that game so well. I know when the bouncing ball should be at its apex and when it's not. And I was happy to see that where it should be. So input. I measured USB and HERA, and it was pretty much the same as any other Raspberry Pi Vice emulator. But I thought, wouldn't it be cool to let people use their real joysticks by just hooking up to the GPIO header with nothing but a DB9 connector and some jumpers. So I did that. I added the code to scan the GPIO headers. You can hook up 2 joysticks, and because the joysticks are pulled right before the emulator enters the next emulation loop, it's pretty much the earliest opportunity to get it in there. Whereas USB, there's an 8 millisecond polling interval, so you can imagine that if things don't line up again, it's kind of a mismatch in timing. If you just enter your emulation loop, you've missed your opportunity, and say the signal went low up to 8 milliseconds before that time, and your polling interval will happen just after you enter the emulation loop. You missed your chance. It's going to get pushed out to another frame. But with polling the GPIO lines, you can get that in there right away, and you get a consistent 2-frame delay. So there's a slight advantage in using BMC64 with the real joystick. So similarly, video latency. I hooked up my oscilloscope again, and just verified here. What you're seeing again is the composite out of the Pi. This little blip here, that's actually this text at the top. So you can imagine this is kind of rotated and it's scanning that. And you can see that there's a mid-frame transition where it goes from dark to light. That's the color change. And you might be wondering, like, well, if the signal was recognized here and I got it into the emulator here, it's gonna have that part of its emulation, its information when it emulates. Why are you getting a mid-screen transition? Wouldn't that transition just happen at the beginning of the first frame? The reason it doesn't is because Vice injects that event, that down event, or the latch change at some random point in the future. And I'm pretty sure they do that. Otherwise, it would be as though you're super accurate with your joystick presses and you're always going to get the signal or the event recognized at the very first cycle of every frame, which would be not right. So on average, you'll get the down will happen, the low event will happen in the middle of this frame, and the recognition of that signal will happen somewhere in the second frame. So I was pretty happy with that as well. Okay, so shutdown. With BMC64, you can just kill the power. Now, why can you do that? I ended up rewriting Circle Standard Library's file system glue layer entirely. And because the default implementation hooked back into Circle's default file system implementation, where they didn't support directories, they didn't support long file names, it didn't have read-write mode. I ended up switching to using a library called FATFS, and I did something on top of FATFS. When the emulator opens a file, it actually opens it in memory. It's all memory backed. If you open a file, or if Vice opens a file, even for read-write mode, it's actually opening it in memory. And all the seeks and writes you're doing it in memory, and only when the file is closed does it flush it to the disk. So even when your emulated machine thinks it's writing or reading to the emulated disk, it's not really talking to the SD card. I kind of defer that flush until later. The downside of that is that if you have a game and you just got your high score and you want to save it, your program might save it, but it won't actually get saved to your virtual disk image until you unmount the drive. But the cool thing is that you can just kill the power. And again, that when you're done your game, or your mom starts screaming at you to get off your computer, you just want to kill the power, right? I just have a mention here that there's no dirty sector write cache, because the files are never really opened for very long on the device. Oh, also there are no background tasks running, right? Vice is the only thing that's running in this scenario. If you run RetroPie or Combien, you'll notice the SD card access. It'll glow every once in a while, and you're like, what's it doing? It's probably running a logging service. But with BMC64, that'll never get accessed unless you're doing something, unless you're mounting a drive or unmounting a drive. Okay, so the last thing. Just make sure I have my in here. So this is a key raw, and I had this in my replica. But again, like I said, I was disappointed this wasn't a power switch. And if you want to hook it up inside a Commodore 64 shell, you kind of have to put on this little USB connector to connect to the Pi, and this is not actually used for power. So I ended up making my own PCB and writing the code in BMC64 to scan the GPIO lines to scan a real keyboard and joysticks to get that advantage of the 2-frame latency, but also to cut the power, because it was really important for me to just be able to click that switch and walk away. And again, it contributes to the feeling that you're using the real thing. So this design is uploaded onto Upverter. They're free Gerber files. You can download them and send them off to PCBWay and make them yourself if you want. I actually don't put these together or sell them. There was someone in, I think, Italy who did make his own version of this and was selling them on eBay. So reception was pretty good. This is how the inspiration for the title of my presentation. Well, it's actually, I guess you could argue that I ripped its sole out and then replaced it with the synthetic sole. But that synthetic sole is pretty close to the real thing. I was pretty happy with the end result, and a lot of other people were too. I posted this way too early. I released this just to lemon64.com way too early. The early versions had a lot of bugs, but it kind of evolved over time. It's the better part of a year. It took me to get to this point. One of the mistakes I made was in an earlier version. I was using when I did my boot optimization, and my 3 cores were supposed to just go to sleep. Well, I called circles a sleep function. Well, big mistake. There is no sleep in bare metal programming. That implementation just did a tight loop. Check the clock. Is it time to wake up? Is it time to wake up? So 3 cores were just spinning, and the core temperature reached something like 80 degrees. And it was still within tolerance, thank goodness, but I was afraid that I was going to start fry people's pies. So I caught that in a couple versions, and I apologize to everybody. So yeah, the perils of bare metal programming. So it's a free open source project. Here are the links. I can switch back to BMC64, but thank you for listening. And if there are any questions, I can take questions. Yes?
Since you're running bare metal, is there no network support or ability to connect it to your home network or to another computer to move files back and forth?
There's no network support yet.
Okay.
And that's something that I would like to add. Circle does support a TCP/IP stack, and I would like to put that in. I actually want to emulate the RS-232 interface, like you can connect to BBSs through a TCP/IP connection. I'd like to support that someday. Yep.
How about the CDM bus?
CDM, sorry, what's that?
The daisy chain bus.
Oh, like hooking up to a real 1541? So that is possible. So there's a library called OpenCBM, and Vice does support that API, so the hooks can be activated. I would have to write the code that, bit bang that protocol, which is all laid out inside the OpenCBM implementation, but there's one for parallel port, and there's one for some custom other implement. I can't remember what it is, but it's possible to do. Somebody brought that up on the forum. I thought, it's kind of going a little further than I would like with hardware. I kind of stopped at the keyboard and joysticks. I don't really see the point other than the nostalgia of, inserting a real floppy disk into drive, but I kind of like the convenience of using an SD card and a USB connector or a USB stick.
You've got HDMI and composite support, but
Yes.
the CSI port or the DPI LCD support for Pi, do those work? or-
So somebody asked me recently if I could get that working. I don't understand it fully yet enough to know, but from what I understand is you add some config.txt parameters to enable DPI. If it's something that the SoC does itself, then it could be made to work. But if it's something that requires Linux, something like a driver, it's not going to be so easy. I would have to port whatever that driver is. So I'm looking into that now. I would have to get a DPI display to try it out. But if it turns out to be something that the SoC does itself, then it should be possible. Yeah.
You touched on this in your presentation, but I assume if you're running HDMI, you could either do PAL or NTSC.
Right.
And if you go to composite output, you're probably limited by the monitor, right?
That's right. If you're using composite, then if it's a PAL machine, you actually need a monitor capable of doing PAL. So a multi-sync monitor or a PAL monitor. Yeah, that's right. Yeah.
Are you involved in any other open source projects? It's a little off course, but just curious if you.
Nothing retro related, but I am. I was contributing to other open source projects. There was a open source Dash player that I was contributing to. I have some on my GitHub link. Yeah.
You said the earlier versions ran mostly on a single core. Is there any way you can get this to run on a Pi Zero?
I do have a version for the Pi Zero. I call it BMC64 Lite. So in the distribution that you can get from the links that I had shown, so on my website you can download a single image now. I used to have one image for every type of machine. I forgot to mention that you do get more than just the 64. You get a +4 emulator, VIC-20 emulator, Commodore 128 emulator. I'll do the PET eventually. And I do put together builds for the Pi Zero, and they will also run on the Pi 1, but only if you overclock the Pi 1. The Pi 1 is just too underpowered to handle most of what the emulation demands. The Pi Zero will also fall over if you throw some really like high intensity demos at it. It will stutter. But for games, I haven't actually seen any games that don't work on the Pi Zero, so if that's all you're interested in, you can try it out. The reason I call it BMC64 Lite is that it sets the expectations that it's not BMC64. I did it as kind of a courtesy to the users on Lemon 64 who were asking for it, because somebody wanted to make their own little Pi Zero Game Boy type of device. So it does work.
I have a little black and white TV with a Pi Zero stuck in the battery compartment.
Okay.
And I'd like to just, at least if I can just get the ready screen flashing on there.
We can try it. I have the SD card if you want to just hook it up and see what happens. Sure. Okay, great. Thank you.